So, hello everyone. Today I'll be giving a talk about groups and permutations. So, as a quick overview of what we will be doing today, I'll first go over what groups and permutations are, along with defining the symmetric group and the alternating group, and explaining some of their key properties. And then we'll explore subgroups, and this will include a discussion of Lagrange's theorem, normal subgroups, and simple groups. And then we'll use what we talk about in groups and subgroups to talk a little bit more about Sn and An, which are the symmetric group and alternating group. We'll prove that Sn is we'll find all the normal subgroups of Sn and An for n at least 5. And to do this, we'll talk about conjugacy classes, and then we'll go over in more detail the proofs of these two properties about the two groups. All right, so first we need to define what a group is. So a group is sort of a useful abstraction for a set of things that also has a operation, which we over here we denote it with a dot, sort of like multiplication. You can kind of think of it like that. So it has the following three properties. There is an identity element 1, where 1 times g equals g for all g and g. And you also have g times 1 equals g for all g and g. And then every element of G also has an inverse, which you can multiply it on either side to get 1. Actually, I forgot to write it, but you should have that. This is also G inverse times G, and this is equal to G times 1. And then finally, we also have that the operation is associative. So if you have 3 things multiplied together, you can do the multiplication in any order. So one thing to note is that groups don't come with multiplication might not be commutative in a group, and that's why we need this extra statement here and here. So we need to add these in our axioms because we want these to be true, but it's not always true that f times g is g times h in a group. And this might seem a bit unintuitive, but you'll see that this is very useful because it allows us to prove properties about many more things if we don't assume that the operation is commutative. And then also we are kind of lazy, so we usually omit this symbol because it's pretty clear what we mean when we're working in a group, that when we put 2 elements fg right next to each other, we're multiplying them together. And since the multiplication is associative, we can also omit the parentheses because you can do the multiplication in any order. So as an example, we have the integers mod n are a group with group operation, that's addition, and the integers mod n are not an operation where or not a group where the operation is multiplication, because in the first case we have the identity is 0, and then everything has an inverse which is negative of itself. And then since the addition is associative, then you get that the operation is associative. But in the second case, we have that 0 does not have an inverse because 1 is the multiplicative identity. Just happened. Okay. Not acceptable. Identity, but then 0 doesn't have an inverse, so that's why this is not a group. All right, so next we have permutations. So a permutation on a set X is just a bijective map from X to itself. So every element gets sent to a uniquely determined element in the set. And then we have a couple related definitions. So you can compose two permutations by sending any input to, you can send it through G and then through F. And then the output of the two things combined would be the output of the composition. And then you also have the identity permutation, where it just sends everything to itself. and we frequently also use E to refer to this identity element as well. We also have that every permutation has an inverse permutation with a property that it being composed with its inverse sends everything to itself. And this always works. There's always an inverse because the mapping is a bijection. So it's both injective and surjective. All right, so our first sort of simple exercise is we can show that every permutation is a composition of cycles. So for each x, there's an index k where if you iterate fk times starting with x, you'll get x back again. And we'll use cycle notation to denote like these cycles. So in this case, it would be like a parenthesis, and then you put the things that are in the cycle in order. This is not like unique because you could have like 1, 2, 3, and you could also have like 2, 3, 1. So these would be the same cycle because 2 goes to 3, 1 goes to, 3 goes to 1, and then 1 goes to 2. And it basically, this cycle means that you have like the first element goes to the second one, second goes to the third, all the way to the end, and then you come back to the beginning. So permutations might have multiple like disjoint cycles and in this case, we sort of just put them next to each other. So if you have a permutation which sends 1 to 2 and 2 to 1, 3 to 4 and 4 to 3, you can write it as 1, 2, 3, 4. Finally, if you have a fixed point, that's sort of like a cycle of length 1. Like in this case, they are usually omitted from the cycle notation. So like this element right here, this could also be an element of permutations on 5 things, and we will interpret this as 5 gets sent to itself. Oh, also, by the way, if anyone has questions at any time, like feel free to put them in the chat. I'll monitor that. Okay. So it is easy to see that permutation composition is associative because, like, in general, if you're composing functions, and permutations are just functions basically, when you compose functions, the composition is associative. So you can just check that like f of g of h of x is f of g of h of x. And then, however, the composition is not always commutative because if we have like x as the first 3 integers, then if you take these 2 elements, you can see that when you compose them in one way, you don't get the same thing as if you compose them in the other order. So f composed g equals 1, 2, 3. This is because you put the elements through g and then you put them through f. So 1 is fixed by g and then 1 goes to 2. So you get 1 goes to 2. 2 goes to 3 and then 3 is fixed. So 2 goes to 3 and then 3 goes to 2 and then 2 goes to 1. So 3 goes to 1. So you get this cycle. And you can similarly calculate the product on this side. Okay. So now we have this notion of a group of permutations. So if you let G be a set of permutations on X, we say G is a group of permutations of X if the identity is an element of G. For each F, we have the inverse is also in G. And for each F and G in G, we have that their composition is also in G. So we can, as a simple exercise, we can verify the group axioms in this definition of a group of permutations, and indeed the first 3 like conditions give us the identity and inverses and closure under the operation, and then we need to verify associativity, but like this is just function composition, so it's associative. And we can see why like it's important that we don't have that axiom about like the multiplication being commutative, because then like this this sort of well-behaved group, like this group is pretty well behaved, but it wouldn't actually be considered a group if we required it to be commutative. Okay, and then we define the symmetric group of order n denoted S sub n. This is the set of all permutations on a set of size n. So normally when we say S sub n, the set of size n, like it doesn't really matter what the elements are, it just matters that there's n total elements. So we normally just let those elements be labeled 1 through n. So for example, in S sub 3, the elements would be the identity E, And then we have the transpositions that switch 1, 2, 1, 3, and 2, 3. And then we have the 2 cycles, 1, 2, 3, and 1, 3, 2. So some more definitions about permutations. A transposition is a permutation that swaps 2 elements and fixes all the other elements. So if we go back here, 1, 2, 1, 3, and 2, 3, these would be transpositions. And then an inversion is like when you write out the permutation, it's a pair ij where I is less than j, but sigma I is greater than sigma j. So basically you have something's less than something else, but then when you send it through the permutation, the ordering gets swapped. And then we define the alternating group of order n, which is denoted by A sub n. This is the set of permutations in S sub n that have an even number of inversions. All right. So one lemma that we have is we can show that the transpositions generate S sub n. What this means is that for any element sigma in S sub n, we can write sigma as a product of transpositions, and we already know that every sigma can be written as a product of disjoint cycles. So if we can prove the statement for a single cycle, then we can just apply it to every cycle that makes up sigma, and then that would complete the proof. So without loss of generality, let's just assume that we have a cycle 1 through k. Then we can just verify that this identity holds. So like we can see that we want to verify 1 goes to 2. So on this side, we have 1 goes to 2, and then 2 doesn't appear anywhere else. So we have 1 goes to 2. And then we can see where 2 goes. 2 goes to 1, and then 1 goes to 3. So 2 goes to 3. And then we can see where 3 goes. 3 doesn't appear here. 3 appears here, so 3 goes to 1. And then 1 goes to 4. So 3 goes to 4. And then we can verify that as you go along this chain, we get 1, 2, 3, 4 all the way to k, and then it wraps back to 1. So this decomposes a single cycle into transpositions, and this means that for any element, we can decompose it into transpositions by just considering the disjoint cycles. Okay, now we'll move on to some lemmas about A sub n. So the first thing we can prove is that A sub n is also exactly the set of permutations that can be written as the product of an even number of transpositions. So it's not even obvious that if you write a permutation as a product of transpositions, you'll get the same parity of transpositions every time. But in fact, this is true. And the way we prove this is that we'll show that the parity of the number of transpositions in an expression that equals sigma is also the parity of the number of inversions. And the parity of the number of inversions is well defined and already fixed. So that would prove our statement. So it suffices to show that when we add on when we compose an extra transposition onto any permutation, the number of inversions changes parity, because then we can start with our base case of the identity, which has 0 transpositions, which is even, and it also has 0 inversions, which is also even. So work in S sub n for some n, and consider the transposition that switches I and j composed on any permutation sigma. So if we first write out sigma 1 through sigma n, then the number of inversions is just the number of pairs of elements in this tuple where a bigger element appears before a smaller element. So, and we also know since sigma is bijective, I and j will appear somewhere. So when we switch I and j in this tuple, that's what the transposition does. This changes the number of inversions by plus or minus 1 when we consider the pair I and j itself, because it either is not an inversion and becomes 1, or it was an inversion and becomes not an inversion. Meanwhile, if we consider any element in between I and j, then that element, once we switch j and I, the inversions that involve it and one of I or j will change by either 0 or plus or minus 2. And the reason we have this is, okay, suppose we have I and j, And first, let's suppose the element in between is larger than both of them. So we have like x, which is, I'm writing it above it because it's larger than both of them. When we switch j and I, since x is still larger than both of them, we can see that the number of inversions doesn't change. And a similar thing holds if x is like below I and j, the number of inversions remains unchanged. And then the more complicated case is when like x is between I and j. But what happens in this case is when you switch I and j, like the number of inversions just decreases by, or in this case, it increases by 2. And then if it's like I greater than x greater than j, when you switch I and j, the number of inversions decreases by 2. So does this make sense so far, hopefully? All right, I'm not seeing any questions, so hopefully I haven't lost anyone yet. But yeah, feel free to ask questions in the chat if you are confused about anything. And then if we have an element that is not in between I and j in this like tuple, then when we switch I and j, like the relative ordering of that element in I and j is unchanged, so it doesn't change the number of inversions involving those as well. So in conclusion, we see that in this case, the parity doesn't change. In this case, the parity doesn't change because there's no change. And then in this case, we have a plus or minus 1. So in total, one transposition changes the parity of the number of inversions. And that proves the lemma. Okay. Now we have another lemma. Show that AN is actually a group as its name suggests. So suppose sigma in Sn is actually an AN, then it must be like expressible as a product of an even number of transpositions by the lemma we just proved. And we know that E is the product of 0 transpositions because it's the identity. So E is obviously an AN. On the other hand, if A is like the product of like 2 K tuples where like each T is a transposition, then we know that A inverse is this thing. And this is also a product of an even number of transpositions, so inverses are in AN as well. We also have that the product of any two elements of AN must be an AN as well, because if you have something that's an even number of transpositions, and you multiply it by something that's also an even number of transpositions, in total, that's an even number of transpositions, and that means that the element is also an AN. So we verify closure, we verify inverses, and we verify the identity. And the associativity is inherited from the group operation in like the bigger group S sub n. So this shows that AN is actually a group, which is cool. Okay, now let's define what a 3 cycle is. It's basically exactly what it sounds like. It's just a cycle with 3 things. So there's 3 elements x, y, z, which are distinct. X goes to y goes to z, z goes to x. Everything else is fixed. So we have the following lemma. The 3 cycles are all in A sub n, and in addition, they generate AN. So similar to when we talked about the transpositions generating S sub n, the 3 cycles generating A sub n means that every element in A sub n can be written as a product of 3 cycles. So first, we can write x, y, z as like this. You can verify this because like x goes to y, x goes to y goes to x, x goes to z. So y goes to z, and then z goes to x. So this is a product of 2 transpositions, which is an even number. So all 3 cycles are in A sub n. We also have that the product of any 2 transpositions, we can do this trick where we multiply by like this thing in the middle right here. That's the identity element, because when you like multiply transposition by itself, you get the identity. So that's where this step comes from. And then we then like group the first 2 elements to get this cycle. And then we group the second 2 elements to get this cycle. Because you have like wx, wy, that's wyx. And then yw, yz, that's yzw. So we see that the product of any 2 transpositions is generated by 3 cycles. But now any element of A any element A and A sub n, we can write it as like T1, T2, and then T3, etc., all the way to T sub 2k. So if we group the transpositions in groups of 2, then each pair we can write it in terms of 3 cycles, and then since we can split it into pairs, then the whole thing is a product of 3 cycles, and this finishes the proof of the lemma. Okay, so this kind of motivates a discussion about subgroups, because what we just saw is that A sub n is like a mini group that sort of lives inside of S of n, and it's like closed. It's also a group, but it's just like a smaller version of S of n. So here we define what a subgroup is rigorously. If you have a group G, a subset H of G is a subgroup of G if H is also a group. And what this means is the identity is in H, inverses are in H, and H is closed under the group operation. So as an example, we have shown earlier that A sub n is a subgroup of S sub n for all n. And another example is the trivial subgroup with just the identity is a subgroup for any group G. We'll also define what a right coset and left coset are. So if H is a subgroup of G, then the right coset for some element G and G is basically what you get when you multiply every element of H by G. And we write this as big H times G. And then the left coset is basically everything you get when you multiply G on the right of an element, or on the left of an element of H. So, and we write this as G times big H. So these two things sort of represent how we write these cosets. And the reason these cosets are important is because we have this nice theorem that tells us that the size of a subgroup of a finite group G is actually a divisor of the size of the entire group. And the way we can prove this is that, okay, we'll just consider left cosets for now. We can show that the left cosets of H actually partition G, and this suffices because then it shows that the size of H must go perfectly into the size of G. So if we let G1H and G2H be two cosets of H and they share an element in common, if we can prove that these two cosets are actually exactly equal to each other, then we are done, because any two cosets will either be exactly the same coset or they'll be completely disjoint, and that's exactly what we want. So from G1H1 equals G2H2, we sort of just multiply by some inverses on each side, and we get that G2 inverse G is H2 H1 inverse. And since H is closed under the group operation, that means G2 inverse G1, since it's like also equal to this product of two things in H, then G2 inverse G1 is also in H. And then finally we have G1H equals G2 inverse G1H, which is equal to G2H2 H1 inverse H, which is in G2H, and that suffices because we have that the coset G1H is now a subset of the coset G2H. But by symmetry, we also have the other way around. So that means the two cosets are actually the same. So if there are no questions up to this point, I guess I will move on. But yeah, this is a pretty important theorem in group theory. So it's sort of good to get like an intuitive understanding about what this, like why the size divides the size of the whole group. It's because it sort of partitions the group into different like sets. Okay, and now we're going to introduce the concept of a normal subgroup. So a normal subgroup is, so let's let N be a subgroup of G. We say that it's normal if for every element in big G, let's call it little g, then we have that the left coset is equal to the right coset of n. And as a warning, this does not mean that gn equals ng for g and g and n and n. It only means that for any g and g and n1 and n, like gn1 is equal to n2g for some other element n2 and n. Like, so that like the cosets are equal as sets, but they're not equal term-wise. That's basically what this is saying. So as an exercise, we can show that the condition for a normal subgroup is also equal to the condition that Gn G inverse is in the normal subgroup for every G in the group and N in the normal subgroup. And the proof of this is pretty easy. We just like take this condition, like this is we get by interpreting what left coset equals right coset means. If we take the n2 as n prime here, we have Gn is n prime G, and multiplying by the inverse of G on both sides gives us that Gn G inverse is n prime, which is in the normal subgroup as desired. So why do normal subgroups matter? Like, why introduce this definition? So one answer is that normal subgroups n of G are special because they can generate a quotient group, which is denoted G over n, and these elements are the cosets of n. So, and the operation of this group is given by, if you have two cosets, Gn and Hn, you have that their product is given by, you multiply G and H together and you take that coset. So one example of this is the integers mod 2, or z over 2z, which gives the quotient group of the integers mod 2, because we have like one of the cosets would be like negative 2, like negative 2, 0, 2. That's the first coset. And then the other coset is like negative 1, 1, . So we have these two cosets as the elements of z over 2z, and we can see that like one is even and one is odd. And yeah, that gives you the quotient group of integers mod 2. So verifying that the quotient group is well defined as indeed a group is not hard, but it hinges heavily on this like thing that we have here where the left coset is always equal to the right coset. And it's not our focus today, so I won't show you guys a proof, but you guys could try to work it out on your own sometime later. Instead, we will use the notion of a normal subgroup to derive some interesting properties about S sub n and A sub n. So we introduce one final definition, which is that we call a group simple if the only normal subgroups of G are like the trivial one and the whole group. And like relating back to this quotient group thing, this tells you that there's no like non-trivial thing you can quotient out by. Okay, so for the rest of the talk, we have these two goals. So our first goal is to show that for n is at least 5, the only normal subgroups of S sub n are the trivial one, the entire group, and the special subgroup A sub n. And then the other theorem we want to prove is that when n is at least 5, the group AN is simple. So these two theorems have pretty deep implications. It's pretty cool. One such implication is the impossibility of the quintic formula, and like despite them existing for quadratics, cubics, and quartics. So if you ever wondered why, it's might be related to these two theorems that I'm showing you today. So to prove these theorems that I just showed you, we need to introduce something first called a conjugacy class. And like this is a complicated name for something pretty intuitive. Like we have this normal subgroup thing where we had like, if n is in the group, then you also have that G and G inverse also has to be in the group. And so we define G1 to be conjugate to G2 if there's an H with G1 being HG2 H inverse. So what does this tell us? This tells us that if G1 is in the normal subgroup, G2 must be in it as well, because we can write it in this form. So yeah, that's why we want to say like this is just a fancy name. You can also think of it as just them being related so that they either have to be in the normal subgroup together or they are both not in it. And we proved the following lemma, which is that conjugacy is actually an equivalence relation. So what this means is that you have these three properties: reflexivity, symmetry, and transitivity. We will go over these momentarily, but each equivalence class, which is a set of elements that are all equal to each other and no other elements are equal to the elements in the class, those are called conjugacy classes. And by the definition of a normal subgroup, this means that a conjugacy class is either entirely contained in the normal subgroup or it's completely disjoint from it. Yeah, so now we prove that conjugacy is actually an equivalence relation. So if you let H be 1 here, you get that G is conjugate to itself. And if G1 is conjugate to G2, if we multiply both sides on the left by H inverse and both sides on the right by H, you get G2 is H inverse G1 H, but H is also the inverse of H inverse, so you can write it in this form. Once you have it in this form, that tells you that G2 is also conjugate to G1. This means that this gives you like the symmetric property. And then we finally prove transitivity. This thing is blocking the view. Okay. But like if you have G1 is conjugate to G2 and G2 is conjugate to G3, then you sort of multiply the two H's that you get together. And when you do that, you get G1 is conjugate to G3. And with that, we have proven the three properties of an equivalence relation. So that finishes proving the lemma. So we have conjugacy as an equivalence relation, and this is important. So as an exercise, we can show that the conjugacy classes in S sub n are elements which have the same cycle structure. And what this means is sort of that like the size of each cycle would be the same. It's just the matter of like what elements are in each cycle. So if we consider all elements of the form A, B, C, D with A, B, C, and D distinct, like these all have the same sort of cycle structure. They're all a product of two cycles. And the claim is that all these are actually in the same conjugacy class. So the proof of this is like, if we let T be a transposition which switches I and J, since T is its own inverse, then we have that T times sigma times T, which is conjugate to sigma. This swaps I and J in the cycle notation of sigma. Yeah, so this is kind of intuitively true. For sort of a more in-depth explanation, you can think of it as like the first T means that I goes to J, then J does whatever J does in sigma, and then J gets renamed to I again, like afterwards. So what this means is that I does whatever J would do in sigma, J would do whatever I would do in sigma, and then everything else does it's like the same thing as it would in sigma. And so that tells you that I and J are in the cycle structure, like I and J are switched in the cycle structure of sigma when we do T sigma T. Now we can repeatedly use transpositions to swap elements in the cycle structure of sigma, and that gives you the claim. Because you can like switch things around and then you'll basically be able to get any A, B, C, D in the cycle structure in this example. And like more generally, you'll just get any element in any order could be like the cycle structure. So a corollary of this exercise that we just did is that all the transpositions are in the same conjugacy class of S sub n. And this is because all the transpositions have the same cycle structure because they're all 1-2 cycle. Okay, so now we move on to proving our first theorem, which is the fact about normal subgroups in S sub n. So if we fix n to be an integer at least 5, our battle plan will be, let's assume n is a normal subgroup of S sub n, and let's also say that there's an element A that's not the identity that's also in n. So but like basically we want to rule out this bad case because like this always exists. So the interesting case is when you have another element that's not the identity. So we will prove that n is either like the alternating group or the symmetric group by proving that A sub n is actually a subset of the normal subgroup. So it's not actually immediately obviously why this finishes, but if we remember that like the number of elements in n, this is a factor of the number of elements in S sub n. So A sub n has a size that's exactly half of S sub n. So this means that like the normal subgroup, if an is a subset of it, it has size that's at least half of the size of the whole group. Now, if it divides the size of the whole group as well, this means that its size must be equal to its size must be equal to the size of the whole group, which means that it is the whole group. Or its size is equal to half of the whole group, but we already know like half of the elements that are in the normal subgroup, so that like uniquely determines n as A sub n. Okay, so now that we have our battle plan laid out, let's try to prove, like, how would we prove A sub n is actually a subset of n? Remember that we proved that the 3 cycles generate all the elements in A sub n. So that means if we can find a 3 cycle in n, then if we just recall what we just did, all the 3 cycles are conjugate to each other. So if we get 1 3 cycle in n, this means that all the 3 cycles are in n, and then n must be closed under the group operation, and the 3 cycles generate A sub n. So that would imply that A sub n is a subset of n, and that would complete the proof. So without loss of generality, let's take our element that's not the identity and write it as 1, 2, 3 to k times b, where k is the longest cycle of A. And like we can permute the numbers in the cycle notation of A, since like this would be in the conjugacy class, to get a cycle of the form 1, 2, 3 to k for some permutation B, which fixes 1 through k. So now we distinguish 2 cases based on the length k of the largest cycle of A. So we basically have 2 cases. So sorry. Okay, the first case is if k is at least 3, then if we permute the elements in the cycle notation of A, we know that like A prime equals B inverse times 1 k minus 1 k all the way to like k minus 2, k minus 3, k minus 4, all the way to 3, 2. This exists in n because B inverse has the same cycle structure as B. Like, oops. This and B have the same cycle structure, and then this has the same cycle structure as the length k cycle that we saw here. Like this 1, 2, 3 all the way to k. That's the same as this cycle structure. Okay, so now by closure, we can multiply A and A prime together since they're both in n. If we multiply them together, the B and the B inverse sort of kill each other. Then these 2 permutations, these 2 cycles, you can check this. You multiply them together, you get 1k, k minus 1. This is a 3 cycle, so we are done. Great. Now, the only like bad case is if all our cycles from before are actually like 2 cycles or fixed points. So A is the product of transpositions on disjoint elements, and then there also might be some extra fixed points. If A is a transposition itself, which means that A is xy, then we know that A prime equals xz is also in this conjugacy class. And then by closure, we have like the multiplied together is also in the normal subgroup. So there's a 3 cycle, which finishes. So now let's assume that like A is not just a single permutation, then it has at least 2 transpositions. And then we know that we can like rename things in the cycle structure. So we can just call it 1, 2, 3, 4, C, where C fixes 1, 2, 3, and 4, and it's also a product of disjoint transposition. So this means C squared is the identity, or C is its own inverse. Okay. Now we'll basically do a similar thing to here where we try to find a conjugate of A that when we multiply them together, we get something nice. So there's two subcases at this point. And here we finally use the fact that n is at least 5. So yeah, it might be weird that you have this n at least 5 like condition, and here it finally shows up. So if A has a fixed point, without loss of generality, you can label this fixed point as 5 by doing the conjugacy class renaming thing. Then if we take A prime to be this, which shares the same cycle structure as A, so it's a conjugate of A, this gives, by closure, you can check this, you multiply the whole thing out, you get a 5 cycle. But a 5 cycle is not a 3 cycle. This is still okay because now we have a cycle that's length larger than 2. So now we can like, we basically just plug this thing, we plug this thing back up into this case. And then the other case is similar. Other cycle, the cycle has to be a transposition, as we know. So without loss of generality, this cycle can be 5, 6. Then if we write the entire like permutation as 1, 2, 3, 4, 5, 6, and then times d, we can again take a conjugate of A. This time we'll take this conjugate. This gives, by closure, that when you multiply them together, you get these two things. And this is also not a 3 cycle, but we are still happy because we now have cycles that are length strictly greater than 2, and then we can plug them back into the first case. And so in both cases, we finally get that there is a cycle, there's a 3 cycle that's in N. So now we know that if N is a non-trivial normal subgroup of S of N, then A sub N is a subset of N, and then we can do this argument about recalling Lagrange's theorem, and we get the two cases. Either the normal subgroup is the alternating group, or the normal subgroup is the entire group. So this finally implies the first of our two theorems. So we have, for N at least 5, S sub N's only normal subgroups are these three things. And this is pretty nice because in general, it's not easy to sort of analyze how the normal subgroups of a big group behave. But in this case, because we're restricting ourselves to permutations, we have a lot of good structure here that we can analyze, and that lets us say this cool fact. And then we have our related fact, which is the normal subgroups of A sub N are only the identity and the entire group, which makes it simple. So we can sort of follow a similar solution path to prove this. We sort of now, understand this condition a bit more deeply. What does this condition mean? This condition just means that if we go back, we can see it just lets us, there's more space to do stuff. That's what N at least 5 means. We have space to spam some extra things into a conjugate, and then when we multiply them together, that lets us get a bigger cycle. And so again, we want to use this condition, which feels weird, but now we know it's just there to let us have enough distinct elements. So as before, we can let N be a normal subgroup of the alternating group, and we'll show that if there's a element in the normal subgroup that's not the identity, then actually there will be all the elements will be in the normal subgroup. And to prove this, we give a short outline. So this step is sort of the same as where we proved that the transpositions generate S sub N, and the transpositions are all in the same conjugacy class. So in the group A sub N, all the 3 cycles are in the same conjugacy class. And although this requires a bit more work, once we get this, then it just remains to prove that there's a 3 cycle in AN. That would imply that the entire conjugacy class is in AN. This should be N. These should be N, sorry. These should be N, okay. So once we get a single 3 cycle in N, then all the 3 cycles are in N, and then by the closure of the group operation, this means the entire group is in N. So N is equal to A sub N. And that will be enough to finish. So we fill in some of the details of the outline we gave. So the first thing in our outline was that all the 3 cycles actually are in the same conjugacy class, and this time we can't use the same trick as we did before with a single transposition on both sides, because like a single transposition is not actually in AN, so we can't use it. Fortunately, we can like spam some like extra transposition that is disjoint from everything, so it doesn't really talk to anything else other than to get multiplied by its own inverse, and it like annihilates itself. So as n is at least 5, then we have enough space to let a and b be extra distinct elements from x, y, and z, and then you can verify that this holds. So we get c is conjugate to its own inverse. Next, we show that xyz is conjugate to ayz, and this completes the proof, because then we can do like, if we want to get from xyz to like abc, we go from xyz to ayz, and then ayz we can go to abz, and then abz we can go to abc. But now we have this formula right here, which is like, basically says that xyz is conjugate to azy by multiplying by like this. And so we also just proved that the 3 cycles are conjugate to its own inverse. So azy is actually azy is the inverse of ayz, and that means they are conjugate to each other. And we already know that conjugacy is an equivalence relation. So this means that since xyz is conjugate to azy and azy is conjugate to ayz, then xyz is conjugate to ayz, and that this completes the proof of this first lemma. So next we have basically the bulk of the proof, which it follows exactly the same way as an SN with some like minor detail changes. So we let A be an element that's not the identity, and we take cases based on the size of the largest cycle. So you can verify in a similar manner to when we're working SN. Now, if we work in A sub n, the conjugacy classes are created by things that not only have the same cycle structure, but to get from one to the other, like you switch an even number of things in the cycle structure. And when k is at least 3, you basically do the exact same argument. You find another element A prime in the conjugacy class, which is forced to be in the subgroup. And then you multiply A by A prime and you get a 3 cycle. And this always exists. You can take my word for it. In the interest of time, since I think time's almost up, we'll just like not go too much in detail over this. It's the same argument. Meanwhile, if k is at most 2, we do another like analogously to our previous proof. We find A prime in the conjugacy class, and then we take A times A prime, which is also in the normal subgroup, and we force it to have a cycle length which is larger than 2, and then we revert back to the first case. And then with this lemma proven, we get at least 1 3 cycles in N, and since they're all conjugate to each other, all of them must be in N. Also, the 3 cycles generate A sub N, so like N is actually the whole group. And this proves the second theorem, which is for n is at least 5, the group A sub n is simple. So this is another very sort of fundamental and like important theorem regarding permutations. Okay. Other topics of interest. So that wraps up our talk for today. And then here are just some extra topics you might want to look into. Like throughout this talk, we sort of assumed n is at least 5. So one thing to like try to do is analyze where the proof fails for n is at most 4. Like you can actually find a non-trivial normal subgroup of A4. And I will leave this as an exercise, I guess, for those who are interested. But the existence of this non-trivial normal subgroup is very surprising, I guess. And then learn more about quotient groups. So yeah, that also gives you some more information about why normal subgroups, like why do we even care about these things. And we can also, you guys should also attend Eric's lecture, which is right after mine. And he will be talking about some interesting things, I think. All right, acknowledgement. So some portions of this talk were based on content that was covered in David Spire's Advanced Seminar on Galois Theory, Promise 2021. And Also, thank you all for listening. So yeah, that finishes the talk for me. Thank you.